Today we're going to move on to section 10.2 and we're going to learn more about our simple linear regression. Our learning objectives are to look at the analysis of variance, which is called the ANOVA. We're going to learn about the ANOVA F test, which is a test of inference. And we'll do some calculations and look back at correlation. Remember, you can stop the video at any time if you need to catch up on notes. Our analysis of variance, and it is abbreviated as ANOVA, allows us to compare several means. Thinking back to the model in section 10.1, if you analyze each subpopulation and whatever value they take on at X, what we're doing is looking at the distributions for the response variable Y, and your line of best fit is connecting all the means for the average response Y. We also converted to a new model, which we said was data equals fit plus residual, and each part of this framework does have some variation in it. When you look at each subpopulation or explanatory variable X, we're looking at the response variable. Of course, there's going to be some variation present, and this is because of the regression line being fitted to the data. Our second source of deviation comes from individual observations themselves. So because each subpopulation records its value for Y, there could be variation about the least squares regression line due to the individual observation. So when you look at the scatter of the observed data and us being able to fit the line to it, we know that we have variation, points above and below our line of best fit. So if you think about the model, we have deviation from all sources, and when you put it together, it looks something like this. So we're going to show where the variation is from for each of these three pieces. So we have variation in the data itself, we have variation in the fit, and then we have the variation itself due to unforeseen factors. We don't want to look at the individual deviations themselves. Typically what we do is we square each of the deviations, and we're going to come up with a method for us to analyze this further. So there's the squared deviations. Each part of this framework goes into what's called an ANOVA table, and it will help you analyze where your variation is coming from. Okay, there's our framework. What we're going to do is convert each of the parts. So the data is going to be called SST. The fit is called SSM. This is the sum of the squares model. This portion represents the fit, which has our slope and our intercept. SSE is the sum of the squares error. This will be the residual portion, our initial variation or deviations. And then SST is the sum of the squares total. This part represents the data. So each of these three parts will be abbreviated in our ANOVA table. So in the ANOVA table, because each of these three pieces is separate, you'll be able to observe where the variation is coming from in each of the two sources and then the grand total as well. Eventually, we'll be running a test of inference, but we said in the last section that if you're looking at simple linear regression and you're going to do a test of inference, we set our null hypothesis to say that the slope beta 1 is equal to 0. If that's true and the slope is 0, that means that all of the subpopulations are actually one giant population, and all the y's can be viewed as being represented by one mean. So we will have degrees of freedom with this model. So we have DFT, degrees of freedom total. We have DFM, degrees of freedom for the model. Because we're working with simple linear regression, we have one explanatory variable. So in this scenario, the degrees of freedom for the model is always 1. Again, one explanatory variable. The degrees of freedom total always has n-1 degrees of freedom. So if we had 12 observations, degrees of freedom total would be 11. And the degrees of freedom for error, DFE, always has n-2 degrees of freedom. When we look at the table, you can actually see how the sum adds up to n-1. We're going to use these values along with the sum of the squares model, total and error, to come up with other parts of our table. So we're looking for the ratio of the sum of the squares to the degrees of freedom. We call this the mean square. If you want to flip ahead in your packet to look at this table, I think it's on page 5. If you want to take a minute and fill in the sum of the squares, these boxes here are missing. Yes, you would be able to calculate everything by hand, but they would be extremely tedious. I'm going to show you how to take the information and extract it, as well as use the iPad to complete our table. If you look at the model, which is our one explanatory variable, we can see here degrees of freedom is 1. Error is always n-2 degrees of freedom. And then the total is always n-1. So if you know any of these pieces, we usually can do some simple calculations to find whatever might be missing. But if you add 1 and n-2, you will get n-1. You can see in the next column, we have the mean square. So we're going to use these ratios here, MSM and MSE, to help us calculate the F test, and then eventually get our p-value. All right, so moving forward in the table, MS is the mean square. We're going to take the sum of the squares, and we're going to divide it by the degrees of freedom. So MST, the mean square total, is going to be the sample variance for Y. I've highlighted in pink MSE. We're going to use MSE as our estimator for the variance for our model, and we can move forward and also find the standard deviation by square rooting this value. Most of this will not make sense until we actually go through an example, and even then I know it's going to be tricky. When we graph our observed data and we fit our regression line, we usually look at R, which is our correlation coefficient. And that tells us if it's a strong, moderate, or weak relationship. Also back in chapter 2, we evaluated the value of R squared. This told me how much of the variation was due to placing the regression line into the data. This value is actually obtained from our ANOVA table. So its accurate value takes the sum of the squares model and it divides it by the sum of the squares total. So we can easily calculate R squared from the information provided. So remember, SST is our total variation and our response variable Y. Sum of the squares model is the variation due to the regression line. And when you look at those together, this will give you a precise value of R squared, which tells us how much variation is present and explained by the linear regression line. We're going to stop there for today. There's no homework. If you have any questions, please give me a call. Have a great day.